Hi, I want to get onto the bonding topic. The bonding topic is a fundamentally important topic because you have to understand how chemicals are bound inside themselves before you can try and then extend that to the properties you expect them to have and the reactions you expect them to have. So we're going to deal with that today. Within Year 9 chemistry, when we start GCSE, I would say this is the most important topic. So there's lots of conceptual understanding, and please make an effort to understand it. Talk to your teachers, read books, go on the internet. You cannot be a good chemist, a good chemistry student, if you don't understand this topic. So get your mind around it. Let's make a start. So I want to start with some revision of my lesson where we were drawing atoms. And I told you that this pattern here, this pattern was really important. And what I'd said was that if you have elements in group 1, then when you draw them, they all have 1 electron in the outermost energy level. Similarly, group 2 elements have 2 electrons. Group 3 have 3, 4 have 4, 5 have 5, 6 have 6, 7 have 7, and group 8 or group 0, noble gases, inert gases, those elements had a full, and that's the important word there, full outermost energy levels. Now, you might think, what's that got to do with bonding? But I'm going to get there. I just need to develop a few points before I explain to you how this links in with bonding. Can we go back and perhaps consider where the metals were? Now, I've grabbed a periodic table off the internet only because the colours were good. The green represents the metals, the yellow represents the non-metals, and can you see the groups 1, 2 and 3 were, that's group 1, that's group 2, that's group 3, and then with the exception of one element, they're all metals. And then let's have a look at 5, 6 and 7, 8. 5 is that group, 6 is that group, 7 is that group, 8 is that group. Those are largely non-metals. So let me go back. Groups 1, 2 and 3 were largely metals. Groups 5, 6, 7, 8 are largely non-metals. Now, this idea of knowing whether an element is a metal or a non-metal will guide you as to how to predict what kind of bonding something's going to have. You must know whether it's a metal or a non-metal. And the most famous example, which I'm going to follow for the next half hour or so, is one of household salt. Household salt is the chemical sodium chloride. And you put it on your fish and chips, etc. The reason I say that about fish and chips is the word salt in chemistry, there are many hundreds of salts. So it's a general term we use in chemistry. However, today the word salt is the common household salt, common name salt, and its chemical name is sodium chloride. So if I think about the bonding that happens within sodium chloride, look at the periodic table, and sodium is there. Sodium is a metal element, and chlorine is there. Chlorine is a non-metal element. Do you remember in previous lessons I was saying that compounds are made from 2 or more elements chemically joined together? Well, I'm hopefully going to join together sodium and chlorine and make sodium chloride as a compound, and I'm going to go through the details of how that happens, and I'm going to then extend these ideas I developed with sodium chloride. I'm going to extend them to lots of other ionic compounds. Let's make headway. Right, so the bonding argument always starts with group 8. Now group 8, group 0, noble gases, inert gases, they are famous for not reacting. Indeed, their name, inert gases, is a function of their non-reactivity. So inert gases don't react. Now let me go back. They are these: helium, neon, argon, krypton, xenon, radon. That last column, group 8, they don't react. Why don't they react? Well, can I go back to this? It's the only group where the outermost electrons are completely full. So the atoms have full outermost electrons. Look, make it clear that you understand that full. That last column, the outermost electrons are full. Now, because they're full, that's why they don't react. In a sense, I don't like to use this kind of terminology, but some people talk about atoms want to have full outermost energy levels of electrons. And yes, it gives you the right vibes that I want you to have. However, there's a better way of phrasing it from a chemistry point of view. You need to say that when outermost energy levels are full, then there is an extra stability with that. So extra stability from having full energy levels. That's the correct way to phrase it. Now, can I draw your attention to having a book on a desk? If I knock it off the desk, it falls down. It's more stable on the ground. So when it's on the ground, it's more stable. When it's on the desk, it's less stable. It's that kind of thing. When atoms have full outermost energy levels, they are more stable. And that's the fundamental point I'm going to use to explain bonding. So let's get back to the slide where we had that. Group 8 does not form compounds. Why? Well, they've already got full outermost energy levels. They are not going to do much at all. Indeed, it was 1961, I believe, when two important events happened. One event, I was born. The other event was that they managed to force one of these group 8 elements to react. They had to put a shed load of energy in. They had to kind of like really force it to react. And they finally managed it after years of trying. It is not easy. You need to expend a lot of energy in order to do something that's not natural. These reactions of group 8 are not natural. They're not going to want to react. And if you're going to make them react, it's going to cost you an arm and a leg in terms of energy to do so. So if you put the idea that atoms have a stability when the outermost energy levels are full, and like that's like really where we're heading with all of our chemistry. We want the chemicals we've got to have full outermost energy levels. We want everything to have full outermost energy levels. When things don't have full outermost energy levels, then they react. They react in order to get full outermost energy levels. If they've got full outermost energy levels, then they're not going to react any further. So group 8 don't react because they've got full outermost energy levels. They're stable. They're not going to want to react with anything. But what about everything else? Let's go back. Everything else has not got full outermost energy levels. Everything else will want to get full outermost energy levels, and everything else will react in order to get full outermost energy levels. It's the stability of the extra outermost energy levels being full that drives reactions, that drives the things that happen in our world. If something's got full outermost energy levels already, then it won't do anything. And that's only the inert gases, that last column. If you ever get asked why that last column don't react, simply say they have full outermost energy levels and are stable. Right, so there is a stability associated with full outermost energy levels of electrons. And this idea drives what can and what cannot happen in our chemical world. Metals, right now, metals. Metals are on the left-hand side of the periodic table. So metals just have 1, 2, 3, they've got just a few electrons in the outermost energy level. Now, how can metals get a full outermost energy level? Well, some people might argue they need to gain electrons. Like sodium might gain 7 electrons. But, you know, there's an easier way. For metals, the easiest way for them to end up with full outermost energy levels is for them to lose their outermost electrons. If they lose the outermost electrons, then there's a complete energy level of electrons underneath. And then that will be their outermost energy level. So metals lose electrons. And they end up with full outermost energy levels. Look, metals have just a few electrons. They lose their outermost energy levels, ending up with full energy levels on the outside. And that's the reason why metals behave as metals. So the behavior of metallic things happens because they lose electrons. And that's really quite an important point. So what about non-metals? Well, non-metals are the opposite of that. Non-metals are on the right-hand side of the periodic table. They often have 7 electrons or 6 electrons or 5 electrons in the outermost energy level. By gaining 1 or 2 or 3, by gaining a few electrons, then their outermost energy levels will become full. And their outermost energy levels becoming full is stability associated with that. So that will happen. So here, non-metals will need only a few more electrons to get full outermost energy levels. They will gain electrons to fill up their outermost energy levels. The gaining of electrons gives non-metals their chemical properties. So metals lose electrons. Non-metals gain electrons. Imagine if you had a metal and a non-metal and you brought them together. Imagine what might happen. Well, I'm going to do that with that example of sodium chloride. Consider sodium a metal element like sodium, and consider it bonding with a non-metal element like chlorine. Then the sodium, this is an atom now. You can go back to drawing atoms video. Here, the Na symbol represents the nucleus. The red blobs are the electrons. The arrangement is 2, 8, 1. 1 electron in the outermost level. And chlorine, it is 2, 8, 7. And what's going to happen is the metal sodium loses electrons. The non-metal chlorine will gain the electrons that the sodium loses. So if that starred electron there were to transfer from there onto this chlorine outermost electron, when it goes into the chlorine outermost electron, then chlorine will have 2, 4, 6, 7, and that one 8. So chlorine can get 8 by gaining that 1 electron. Sodium can get 8 by losing that 1 electron. And then both of them have got 8 electrons in the outermost level, and they both then have full energy levels. This is what happens when a metal-non-metal combination come together. Let's just focus a little on just the sodium. What's happening to that? That's the sodium, 281, electronic configuration 281. When it loses that 1 electron, it forms a sodium ion. Now, sodium ions, they're positively charged. Can you see? Sodium, we put the charge in the top right-hand corner as a superscript. So, how do you show them in dot and cross diagrams? You're commonly asked to do dot and cross diagrams in exams. And here you've got red blobs. But if you're doing it, you can put dots or you can put crosses. And dots are acceptable, crosses are acceptable. Indeed, red blobs are acceptable if you can be bothered. So how do you draw atoms? Well, you draw atoms like this. How do you draw ions? Ions are charged. That's the difference. Atoms are neutral, ions are charged. To show a charge, you must put in that top right-hand corner, you must put the size of the charge, and in this case, it's 1 positive. Now, why is it 1 positive? Well, that electron is negative. It's 1 negative. If you lose 1 negative, then 1 positive is the charge that's on the ion. If you want to count deeper than that, then you need to go into the nucleus. The nucleus has got 11 protons. Here, there are 11 electrons, and the protons are balanced by the electrons. But on this side, you've still got the same nucleus, 11 protons, but now you've only got 10 electrons. 11 positive charges, 10 negative charges. The balancing act is that here there's 1 extra positive charge, and that extra positive charge is shown in the ion as a positive charge. So ions are formed by losing, in this case, or in future cases losing or gaining electrons. And the number of electrons they lose or gain will give us the size of the charge that that's going to have. So sodium, 1 positive as the ion. What about the chlorine when all this is going on? We knew the sodium loses an electron. Here, the chlorine atom. The chlorine atom was 287. It's gained another. See that 1 electron there was on its own, and here it's paired up. That's the electron that's come from the sodium. That sodium electron joins it and turns it into 288. The charge, chloride ions, are single negative. Look, square brackets, single negative charge in the top right hand corner. You can count up protons. There's 17 protons in that nucleus, 18 electrons, so 1 more electron. Electrons are negatively charged, 1 negative charge. These are supposed to be square brackets. So you show ions by putting square brackets and the charge in the top right hand corner. And both of these sodium ions and these chloride ions are being formed at the same time. So when metal elements bond with non-metal elements, that's classic example of sodium and chlorine that we've got, there will be electrons lost by the metal. So in the example, sodium loses electrons, and those electrons are gained by the non-metal. So in that case, the chlorine gains the electrons. This electron transfer by lots of atoms, it's not just the 1 atom I'm drawing, there are trillions of atoms. They all lose electrons, and they all form ions, positively charged. Positive and negative ions which naturally attract each other. So the sodium ion, positive, the chloride ion, negative, the positive and negative attract. That attraction is ionic bonding. That is the crux of the matter. The crux of the matter is that the electrostatic attraction as a posh phrase simply means electrical attraction between positive and negative. Where you've got positive and negative charges attracting, we call it electrostatic attraction. So this electrostatic attraction between positive and negative ions, that is ionic bonding. And you know what? You've got to know that ionic bonding is strong. And that strong ionic bonding is what holds the ions in their place. So let's look at the structure. Let's look at the structure of sodium chloride once you've got the ions. Once you've got trillions of positives, trillions of negative ions, then how do they arrange themselves? Look, here, I've grabbed grabbed an image. Can you see? The reason I like the image was it was a cube. It looks cubic. Indeed, sodium chloride structure is cubic. The yellow balls are chloride ions. The purple balls are sodium ions. I know that because the yellow balls are bigger. The chloride ions are bigger. The sodium ions are smaller. And the same number of sodium ions as there are chloride ions. And although this is cubic with 3 by 3 cube, you might argue that there's 9 ions in that layer and 27 ions in total. But that's just a tiny bit of the structure. The real sodium chloride structure goes on for trillions by trillions by trillions. They're not small. Even your smallest grain of household salt is composed of many, 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 many trillions of positive and negative ions arranged like this. And can you see they alternate? The positive, negative alternate. There's never 2 ions the same next to each other because they would repel. Now, you will argue, if you're intelligent, you'll argue positive and negative attract. But that positive and that positive will repel. That positive and that positive will repel. That negative and that negative will repel. And yes, you're right. There will be lots of attractions. At the same time, there will be lots of repulsions. But in order for all these chemicals to actually exist in the real world, the attractions outweigh the repulsions. The repulsions must be smaller because look, they're on the diagonal. The diagonal distances are longer. So the repulsions being further apart, overall, if you add them up, there are less repulsions than there are attractions, because the attractions, the ions are right next to each other, attracting strongly. The attractions outweigh the repulsions. And that will happen in every ionic compound that we come across like this. So, whenever we have metal-non-metal combination, we'll get ionic bonding. The positive ions are next to negative ions. They alternate within a huge 3-dimensional repeated pattern, which we call a lattice. Now, that phrase lattice is used a lot in chemistry. That phrase lattice means repeating 3-dimensional pattern. Repeating 3-dimensional pattern is a lattice. So you need to be able to draw sodium chloride structure. And we're only talking about drawing a small bit, a small cube. You need to be able to extend these ideas to other examples, which I'll point out a few more examples, but hopefully if you understand sodium chloride, you will be able to extend the ideas to other compounds. Now, one of the hardest things boys find is drawing sodium chloride. So I'm going to show you how to do it very quickly. Get a piece of paper and a pen and practice it. Pause the video and practice it. It all starts with you knowing that sodium chloride structure is cubic. So you start by drawing a cube. Look. First, in pencil, draw a cube. Then, on the corners, these corners, I want you to put a chloride ion with a circle. Chloride ions are bigger, so circles are bigger. We're going to use blobs for sodium ions. So circles on the corners and 3 circles in the middle of the faces. One there, and one there. So faces and corners, I want circles. Watch. There. Circle, green circle is a chloride ion. The corners and the faces, they're just the chloride ions. Now we need the sodium ions to finish off. Here. The sodium ions are the red blobs. You put the red blobs between the green circles. So the red blobs are the sodium ions. And there, can you see they're between the green circles. And that gives you that alternate structure that you need. And finally, you finish off by adding a key or a legend. And that's my key there. So the final drawing should be that. Even if you're not good at drawing, you should be able to do that. Occasionally, probably about once every 5 years, the exam board will set a question and say, draw the structure of sodium chloride. They won't ask you to draw anything else because other structures are different. You get different shapes. They can lead to different crystals and different shapes, etc. And people regard drawing those as being really difficult. They do not regard this as being too difficult. So, if we know the structure, like strong attractions between positive and negative ions, then we should be able to link that to the properties of those compounds that have this kind of bonding within them. So, when you understand the structure, you should be able to link it to the properties. Now, there are 3 properties, and I'm going to run through the 3 properties, and we're going to apply these ideas to this kind of bonding today, ionic bonding. And then in future lessons, we're going to apply the same ideas to covalent bonding and metallic bonding and any other kind of bonding we get. These are the questions that the exam boards tend to ask about. So they ask about whether something's going to conduct electricity. Now, there are only 2 reasons why something conducts electricity. Reason 1, it's got in it free ions. Reason 2, it's got in it free electrons. So free electrons or free ions, either of those will conduct electricity. And where you haven't got those, if you don't have those, no conduction possible. So all we need to focus on is, do we have free ions? Do we have free electrons? If we do, conducts. If it doesn't conduct. So learn that. Learn the fundamental thing for electrical conductivity is either free ions or free electrons. Then they ask you about melting points, boiling points. Well, you've got to learn that the melting points and boiling points will be high if the bonding between the particles is strong. And I've been saying this kind of electrostatic attraction is strong, and therefore, if it's strong, then you need a high temperature. The melting points are high, the boiling points are high. It's very hard to get them to melt, very hard to get them to boil. And when you are using very high temperatures to get them to melt and boil, only those very high temperatures you need them. You need those very high temperatures in order to overcome the strong attractions. If the attractions were weak, a low temperature would break them. If the attractions are strong, then you need a high temperature to break them. And finally, one that I don't particularly like because it doesn't have a straightforward answer. Do the chemicals dissolve in water? Now, if they dissolve in water, then the particles tend to break off and the particles are then moving around freely inside the water. If they don't dissolve, then the particles don't break off. The particles stay together and they form, if it's a solid, they sink to the bottom. If it's a liquid, it might just be an immiscible liquid floating on top, etc. So understand that they're the things we're going to be asked questions about. And then applying those ideas to ionic compounds directly, we get the following ideas that you need. So ionic compounds, they all have high melting and boiling temperatures. Why? Because their attractions are strong. Look, due to strong electrostatic attractions between positive and negative ions, high temperatures are needed to overcome these strong electrostatic attractions if the chemical is to melt or to boil. Consequently, ionic chemicals are all solids. They're all solids because normal room temperature is not enough to melt them. You need high temperatures to melt them. You need high temperatures to boil them because they've got high melting and boiling temperatures. So they've got high boiling points, melting points. Right, conduction of electricity. Do ionic solids conduct? Ionic compounds, solids do not conduct. Why? Well, all the electrons are in energy levels, so there are no free electrons. We come across free electrons with metallic bonding, not ionic. In ionic, there's a transfer of electrons, but the electrons are in energy levels. When they're in energy levels, they're not free. Inside an energy level is inside an energy level. It's not free. So, the only thing left to ask is, are the ions free? In the solid, the ions are held in their place. The ions are vibrating. They're not moving about. Fundamentally, they're not moving about. This was the first lesson that I ever delivered on Year 9 chemistry. The particles of a solid stay in their place and they vibrate. They do not move about. So the ions are firmly held with strong electrostatic attractions in their places. And so conduction is not possible. No free ions, no free electrons. Does not conduct. That's solids. What if we melt them? What if we get a high temperature and we start with household salt and we melt it? Melted salt. Now, melted salt, that will conduct. What if we get salty water? We put salt into water. That will conduct. So look, ionic liquids, ionic solutions, even ionic gases, which you won't come across. But I thought I'd include it for completeness. Ionic gases, ionic liquids, ionic solutions, all of them will conduct electricity. Why? Well, because then the ions, they're ionic, the ions will be free to move about. If the ions are free to move about, these free ions will be responsible for electrical conduction. And the next lesson, I'm going to pull up some demonstrations to demonstrate these things and actually see if I can get solids to conduct electricity or melt some solids. It's a bit of a harder practical to do, but I've got a solid I can melt, and I can show you then once melted, it does conduct electricity, and I can pass electricity through salty water, showing you that it conducts, etc. So when the ions are free, then these things do conduct electricity. Finally, dissolving. Ionic compounds, many of them will dissolve. And when they dissolve, the ions end up freely moving about in the water, going around each other amongst the water particles. If it doesn't dissolve, they don't all dissolve. It's normally because the attractions are so strong. If they're really strong in water, the water can't break down those attractions. If the attractions stay, and the positive, negative ions stay together, then it will just sink. It will not dissolve. It will not break up into ions. The ions will not spread out amongst water, etc. So what can I tell you? Well, many ionic compounds dissolve in water. So many do dissolve, but some do not. Water will break down the lattice structures, and the ions will then move freely within the water. We will then see the solid dissolving. However, if the electrostatic attractions are too strong, then the water will not manage to break down the lattice structure, and the compound then will not dissolve. So these properties follow on from understanding the structure, and you get questions on papers as a consequence. So to finish off, final slide. NB is nota bene. Now that means take good note of. I use it when I'm teaching and I say this is important. I will precede it with this NB. NB, nota bene, that take good note of the following points. So ionic bonding happens when a metal, non-metal combination of elements join together to make a compound. The second point, really important. Ionic compounds have particles that make them up called Ions. So many of my boys don't know that it's ions. It's ions. It's ions. Ionic bonding. The particles present are ions. Ions. Ionic bonding. The ions attract each other strongly in a lattice. Their arrangements give their crystals a particular shape. So I was saying you can draw sodium chloride as a cube. Well, crystals of salt are cubic. Go home, get some salt, put it on the palm of your hand, have a good look. You'll see that they are perfect little cubes, teeny weeny little perfect cubes. That's because the structure is cubic. Other ionic compounds will have other shapes. Crystals have different weird and wonderful shapes. The shapes are determined by the arrangement of the positive and negative electrons. The smallest of our crystals will contain trillions of ions. So atoms are tiny. Ions are therefore, similarly, they're tiny. They're of the order, in terms of size, that atoms are. And therefore, you will get trillions of them in the smallest speck. And they spread out in water. Arguably, if you think about 9 million chemicals are documented, then how many of them are ionic? Well, about 500,000. About 500,000. So this is a really important type of bonding, but there are other compounds that don't have this kind of bonding. And that's what we're going to deal with next time. It's going to be called covalent bonding, but I think next I'll do a practical session on some of these properties, and then I'll get into covalent bonding as another type of bonding. That the majority of compounds in our world are covalently bonded, not ionic bonding. But don't get me wrong, 500,000 chemicals ionically bonded is a shed load of chemicals, and many important chemicals you'll come across in your everyday life and exams, etc. This is one of the major types of bonding. Learn it, understand it. See you next time.